Hello everyone. In this video session, we'll discuss about variety of situations as far as viscosity is concerned. The first one, an object sliding along horizontal plane on a thin oil film by force F. Okay, here you can see that I have shown a horizontal plane. Above that there is a thin layer of oil of thickness t, and there is a block, right? The block has got obviously length, breadth and thickness. Actually, when it slides, it will be sliding on this rectangular place, which has got an area, length multiplied by width. But generally when we draw the sketch, this is not the surface that will be in the sketch. I'll try to show even that also. So this is how we draw the picture. We show the thickness is not coming in contact with oil. The length multiplied by breadth, that area will be coming in contact with the oil or whatever liquid that is there. Okay, here when you apply force F, obviously let us say this starts moving. When it starts moving with some constant velocity v, right, under the action of force F, if it is moving at a constant velocity v, that is to say this F is nullified by a viscous force because of viscosity, and this force and this force must be equal so that there is no resultant force exerted, so you will have velocity a constant and acceleration 0. We'll see the same thing here. Newton's law of viscosity states that the shear stress is directly proportional to velocity gradient or rate of shear strain, and that is given by du by dy or v by t, we say, because this is moving with a velocity v, and here at the surface of contact the velocity is 0, so linearly when it moves it will be v by t. Anyway, we'll go into those details afterwards. Now when it is directly proportional to du by dy, the shear stress is equal to mu, the constant of proportionality, into du by dy, and this is also written as tau is equal to mu multiplied by v by t. V is the velocity and t is the thickness of the fluid that is in between. The velocity at the contact surface here, stationary surface, will be 0, and here it will be v, and because of that linear variation we can say that the rate of strain is v by t. Tau is shear stress, mu is dynamic viscosity, v is the velocity of moving layer or moving object, right? T is the thickness of the liquid between stationary and moving layer. For a constant velocity of motion, acceleration is 0, sigma f is equal to 0. In this picture, f minus fv equal to 0. Fv is viscous force, which is given by shear stress multiplied by the area. I told you, L multiplied by the breadth. This way, this thickness or this area is not coming into picture at all, because the area which is having a contact of fluid will be this area, which is very thinly or not even shown when the diagram is drawn. So tau into that area will be giving you viscous force. So overall what we can say is applied external force is equal to mu into v by t into area. You can calculate any of the unknowns from this one equation, and this is the case where On a horizontal surface, on a horizontal surface, the for force, the object is moving. Okay, we'll go to the next uh, important slide. Here, this is the equation to be remembered. When they coin a problem, they may ask you any of these five variables given the other four directly or indirectly. Okay, next is an object sliding along incline on a thin oil film. So this is the thin oil film that will be there. An object is moving with a velocity v on its own weight, right? There is no force. This arrow is nothing but velocity. So this is not a force which is trying to push it. The component of velocity, component of weight will be trying to push it down. So whenever there is a oil film which is in contact, obviously there will be a viscous force which will be acting in a reverse manner. If the velocity is constant, again the same argument applies here. That is, a component of weight which is pushing it down should balanced by Fv. We'll try to see that here. So as I told you, this thickness or this height is not the one which comes in calculation. The other dimension which will be coming in contact, right? Now here, vertically downwards is W, right? And angle with horizontal, we can put it as theta, or sometimes written as x. So here I can write it as theta, so this will also be theta. So this will be W sine theta. That is, W is this theta, so this will be W cos theta, which will be trying to push the object towards the surface, whereas this component W sine theta will be trying to push it down the plane, and because of this component the object is moving downwards, so there will be a resistance offered which will be because of viscosity of the liquid, and that is Fv, viscous force, and this is acting on an area of L into B, where L is this length, B is perpendicular to the surface of the board, right? So W sine x, the component parallel to the incline, helps the object or helps the block to move down the plane. This is the one. The block moves with a constant velocity downwards. Because of that, the force has to be equal to 0, right? The same analysis is shown once again. Here everything is written. The object weight is W, slides down the incline, theta is the inclination with horizontal, here theta, a constant velocity v, the contact area is A, this is not being seen here, liquid thickness of T, that is this thickness is T, and is given by, for a constant velocity, acceleration is 0, sigma f equals 0, this is along the incline, that is along the incline. So W sine x minus Fv equal to 0. So Fv is mu v by d A, you know that, right? This is shear stress multiplied by area will be giving you shear force. So from this equation, if I write equation for V will be equal to this Fv, which is nothing but W sine theta, multiplied by T divided by mu into A. So that is the equation. Again, on this equation, there may be number of numerical problems asking for only one unknown to be calculated, because it is only one equation which has to be solved, right? So there will be a variety of questions formed to use that particular equation. So when the object moves like that, obviously there will be viscous force. So W sine theta minus F equal to 0 is the major equation when the object is sliding along the incline on a thin oil film by its own weight with a constant velocity. So W sine theta is equal to Fv, and if I substitute even Fv with mu v by t into a, one can end up with this kind of equation. So one should remember both of these equations. Okay, next, the power lost in viscous resistance during rotation of a rod in a sleeve. There will be a number of mechanical devices where a rod is being rotated in a sleeve, right? So that situation is shown in the form of a picture over here. So this is external blue one is a sleeve of length L and a rod of some good length which will be passing through and through. It is shown in section, because of that it is being seen as just a circle, right? So the rod of diameter D rotates with RPM n, means this is rotating at an angle of rotating at a speed of n, that is revolutions per minute. Now oil film, between this sleeve and then rod there is an oil film. The oil film has got a thickness T. Now when I try to draw a free body diagram for this rod, it will be like that. So this is oil film, the yellow one is oil film. The same oil film is shown here. This is the rod having a radius R, and then when this rotates like that, when it rotates like that, there is a oil film, and then external to oil film there is a sleeve which is stationary, and this is moving. Obviously when it moves there will be a kind of viscous resistance. This will be rotating like that, right? So what we are interested ultimately is the power lost in viscous resistance during rotation of a rod uh, when it is rotating in a sleeve as given. So P, the power lost, or power is equal to pi nt by 60. This is a regular formula. Now what is the torque which leads to the loss of energy? We'll see. N is revolutions per minute. Now here when it rotates, obviously there will be resistance because of viscous force, that is Fv, right? Now because of that force Fv at a distance of r, Fv into T will be nothing but a torque like that, right? Fv into T will be the torque. So the torque will be equal to Fv into d by 2 or Fv into r. Okay, now the viscous force Fv itself is given by, again it is stress multiplied by area. The shear stress is given by mu into du by dy or mu into v by t. Mu v is the velocity of this, and t is the thickness of the oil film. Okay. Now the linear velocity v, which is at a distance of, here it is shown, when the rod is rotating, this particular point, if you take it, is moving with a linear velocity, which is given by v is equal to pi dn by 60. You know that v is equal to r omega. R is the radius, omega is nothing but angular speed given by pi n d by 60, right? V is pi n d by 60. Okay, now by substituting all the expressions in the first equation, we get P is equal to pi cube d cube n squared mu L divided by 3600 T. So This is a ready-made equation rather than doing all this earlier one by one equations. It is only one equation which relates all with the power lost. D is the diameter of the rod, N is the RPM with which it is moving, mu is the lubricating liquid dynamic viscosity, mu, the L is the length of the sleeve, T is the thickness of the oil film, or whatever gap that is there here, that will be nothing but T. So power lost is P, D is the diameter, L is the length of the contact, T is the thickness of the oil film between rod and sleeve, mu is the dynamic viscosity of the oil. Okay, that is the equation to be remembered. Thank you. We'll stop here.